So we are going to see the numerical based on the bolted connection. So firstly we will just write the numerical. Compute the design strengths and efficiency of a bearing type connection. The grade of bolt used is 4.6 grade and 20 mm in diameter. Plates are of Fe410 grade. So this is our numerical. It is a simple short numerical. Only the thing is that one diagram is given in this numerical. As you can see in this diagram, the two cover plates are there, and in between these two upper and lower cover plate, there is a main plate at the center. Okay, and there are four rows of the bolts used here. This type of what you can say a bolting layout is there. So we can also draw the top view of this type of connections. So there are two cover plates. One is T1 and one is T2. T1 is having 12 mm thickness, T2 is having 8 mm thickness. The bolts are given. Now the thing is that whenever such type of plate is there and this type of force is there, then if such bolts are there, then the distance between these two bolts is what your pitch is there. After that, this pitch is there. This is your end distance and this is your edge distance. Okay. Now what is the difference between the end distance and edge distance? Along the force, parallel to the force, you are having the end distance, that is E, and along this edge you are having the edge distance. So this is the difference between these two. This is your end distance and this is your edge distance. Okay, this is your force and that force will be your tensile force in this case. The distance between these two rows of the bolts is pitch. Okay, now after that, here also you are having such type of bolts and the distance is also given here. So this distance, the distance between these bolts and again the distance from this center is also given. So this distance is 35 mm, this distance is 65, this distance is again 35. Okay, so this type of things are given in this numerical and this is your main plate in top view. And in top view you can have this symmetrical shape. All the things on left side will be equal to all the things on right side. Okay, some more distances are given, that is this distance, this will be your 120 mm distance, this will be 120. After that again this distance will be there, this distance will be 35 mm again, and this distance will also be your 35 mm. Okay, so this type of things are given. Now this type of diagram is complete. Now we will move further, we will try to solve the more things now. What we need to find, the design strength and efficiency. This is the given condition. Okay, now how to find the design strength? That is the VDSB, design strength. Either it may be shearing or bearing. Okay, so shearing strength of bolt, the formula for shearing strength, that is VDSB. Already we have seen it in our previous lectures. VDSB is equal to FUB divided by root 3 into MB, gamma MB, sigma MB multiplied by NN into A and B plus NS into ASB. So this is the formula for bearing strength of the bolted connection. Okay. Now, what is going to happen here? How is your bolt that is not given? So that's why if such type of bolt is there, then what we will consider that this whole bolt, we will consider it as a threaded section. We are not considering the shank anywhere. Okay. So therefore, how many shearing planes are here? At this location, top plate is there, here you can see, and bottom plate is there. So here is one shearing plane, and at the bottom there is another shearing plane, because there are total three plates. One is at the bottom, one is at the bottom, one is at the top, and one is at the center. At the center there is the main plate, then 12 mm thick, that is the top plate, then 8 mm thick, that is the bottom plate. Okay, so three plates are there, that's why there are two shearing planes which will cause the shear on the bolt. And we are here considering whole bolt as a threaded section. Then in such case, what is going to happen? Your n value will be equal to 2, and the value of ns will be equal to 0. That is, number of shearing planes on the shank will be equal to 0, because there is no shank. As per our assumption, we have considered the whole bolt as a threaded section, so that's why the value of nn will be equal to 2 and value of ns will be equal to 0. So the formula will again get modified now. Okay, so as per your IS codes, the minimum pitch here equal to 65 mm. So that's why 65 mm can be written here. Minimum end distance E is equal to 35 mm. We have written 35 in our top view diagram. Now, how many number of bolts are there? On one side there are 4 bolts, left side, and on right side there are 4 bolts. So the force acting on left side is also there, and the force acting on right side is also there. On both sides the force is acting, right? So therefore you are getting this strength for only one bolt, but for connection you need to multiply it with the 4. So that's why you need to multiply the shearing planes with the 4, because there are 4 bolts here on one side. Okay, how many shearing planes you are having for single bolt? For single bolt you are having the 2 shearing planes. So for 4 bolts you will have the 4 multiplied by 2, right? So 4 multiplied by 2, because you are having the 4 bolts on each side, so that will be 8. So total shearing planes will be 8 for one side, and total shearing planes will be 8 on other side. So as the force is acting on left side and right side is different, so that's why we will calculate for only either left side or right side. So you only keep this thing in your mind, that the number of bolts on any side you have to multiply it with the shearing plane. So if shearing planes are 2, then 2 multiplied by 4 is equal to 8 for one side. We are calculating strength for only one side. Okay, now what is the A and B? The value of A and B. A and B is nothing but your area of bolt in threaded section. So in threaded section, you know that the area got reduced. So therefore, the formula as per your code is 0.78 into ASB. And what is the value of ASB? ASB is pi by 4 d square, right? Pi d square by 4. Okay. So therefore, you will get this value of A and B 0.78 multiplied by pi multiplied by 20 square by 4, because your diameter given is 20 mm. Okay. Now you will get this value of VDSB. If you put all the values, you will get the value of VDSB as FUB. What is the FUB? FUB is your ultimate strength of the bolt. So the ultimate strength of the bolt assumed as, for 4.6 grade, you are having the 400 MPa strength. That is Newton per mm square, MPa, megapascal, as per your table in the IS code. Okay, you can refer. I have also shared with you the various codes. So side by side, you can study that codes. As per that code, for 4.6 grade, your ultimate tensile strength is 400 MPa. Directly, this value is derived from that table, 400 divided by root 3 as per this formula, multiplied by gamma MB, that is 1.25, that is partial safety factor for the bolt. Now, what is this partial factor of safety? For bolt, the factor of safety is different. For plate, it is different, right? So that's why this is not the whole factor of safety. It is only limited for your bolt, and that's why it is called as the partial factor of safety for the bolt. That is the thing. Okay, so that value is 1.25 again. Already we have seen this, multiplied by 2 into 4, that is 8, multiplied by A and B, whatever the value that you will got here for the A and B, you substitute that value, and at final you will get this value for the VDSB. After substituting all the values, you get this value near about 362.17 kilonewton. You will get the value in Newton, then you multiply it with the 10 raised to minus 3, you will get the value in kilonewton. So this is the value for your shearing strength of bolt. Shearing strength of bolt. Now after that, the second thing what you need to do is